Good day, guys. Abstract Algebra 2. So in the last video, we talked about groups, definition of rings, how to show that a set is a ring. We talked about integral domain, zero divisors, and what again? I think we talked about integral domain, nilpotent and idempotent elements. So today we are supposed to be moving down to associates, cause and associate, sub-rings and ideals. But before we do that, there are some basic things you have to do before going into that. So the first thing I will do is prove that prove that the additive inverse of a ring is unique. So remember, from definition of a ring, the first thing you have to do is to define closure property for both addition and multiplication, associativity, addition and multiplication, commutativity just for addition, existence of zero element, distributive property. So what we are trying to prove here is that, remember from your one of the definition of a ring, that for all A in R, there exists a minus A such that A plus minus A minus A plus A equals to 0. So we are trying to say that the additive inverse of a ring is unique. That is, there exists one and only one additive inverse in a ring. I can't have two or more additive inverse in a particular ring. That's what they mean by unique. So if I'm going to prove that, so I'll start by saying let R be a ring on both addition and multiplication. Let this be a ring. Then I will assume that there are two additive inverse. So first of all, I'll first say let A, let's say let A be an element of R, and let A inverse be its additive inverse. So similarly, I can also say, if possible, I'll take another one, that this should also be another additive inverse. Another additive inverse of A. Now, from the first one, this is the first one, and this is the second one. So I want to show that the additive inverse of a ring is unique, but I'm proving by contradiction that let's assume that this A, that is an element in a ring, has two additive inverse, this and this. So from one, so since this is the additive inverse of A, then I can show this, that is A plus the additive inverse equals to, which is equals to 0. I can call this equation 1. So you can write beside it, you can just write something beside it, no space there, that a ring is an abelian group so by definition, what I mean is that by definition of existence of additive inverse, so we know that A plus minus A equals to minus A plus A, which is equals to what? 0. So basically what you are trying to do here is that you are trying to explain what you wrote here, just like you are doing circle geometry. When you have let's say this side is opposite to this side, right beside it, A is equals to B. Why? Because they are opposite to each side. Okay. So similarly, I'm also going to do the same thing for this. Then I can say that since let's say A prime is the additive inverse of A, then by definition, then I can say A plus the additive inverse of A equals to 0. Then I can also write same thing here. What I wrote here, I can easily put it here that let R plus times be an abelian group, blah blah blah, like that. Now, this is let me call this one. Let me call this equation 2. So from 1 and 2, that is from equation 1 and equation 2, we have that A plus A inverse, the different additive inverse here, equals to this here. So I can basically say that A minus A plus A inverse equals to, and this is coming from by definition, we have what we call left cancellation. So what I basically did was to subtract A from both sides. So A minus A will give me 0, A minus A will give me 0, then I can see that A inverse equals to A. So basically, the assumption that this element A has a different inverse and also here has a different inverse, I've been able to prove that the inverse is unique, that is, this is equals to this. So additive inverse of a ring is what? Is unique. I can't have 2 or more additive inverse for a particular element in a ring. So if I pick out maybe 4 from an element an element from a particular set R, which is a ring, the 4 can have 2 or more additive inverse. So what I did was to assume that the element has 2 additive inverse, and I've been able to prove at the end of the day that my assumption here and my assumption here are both same. So from here I can say that thus the additive inverse of a ring R is what? Is unique. Okay. So now the next thing I want to move into is an element A in Zn is a unit if and only if A is relatively prime to N. So first of all, what do they mean by a unit, and what is the meaning of relatively prime? So basically, from definition of unit, of a unit, so we say that let R be a ring with unity. That is, when I say let R be a ring with unity, what I mean here is that identity, that's one. An element, let's say an element U in R is called a unit, if there exists a V in R such that UV equals to 1, which is equals to VU. So an element U in a ring is called a unit if there exists another element in that ring, which is my V, such that when I multiply the two of them together, I'm going to have 1. let's take for example, if we are asked to find, let's say, find the units in, let's say, let's take for example, um, maybe Z6, maybe Z, let's say Z5, let's say Z5. So if I'm to find the unit in Z5, if I draw a modulo table, I have 0, 1, 2, 3, 4, 1, 2, 3, 4. Those are the residues in the Z5. So from definition, U times V equals to 1. So let's see, 1 times 1 will give me 1. This will give me 2. This will give me 3, 4. This will give me 2. This will give me 4. This will give me 1. 2 times 4, 8. That's 3. This will give me 3. This will give me 1. 3 times 3, 9. That's 4. 3 times that's 2. This will be 4. This will be 3. This will be 2. And this will be 1. So now if you look at it now, you see that from my table, 1 times 1 gives me 1. So unit in Z4, the first one I see here is 1. When you look at it, 2 and 3 gave me 1. So basically it means 2 and 3 is also a unit in Z5. And then, okay, 3 and 2 is the same. So 4 and 4 also gave me 1. So I also pick what? 4. So the units in Z5, they are what? 1, 2, 3, 4. Why are they units in Z5? Because when you basically look at it, you see that they follow this definition. So that's what they mean by a unit. So now, what do they mean by relatively prime? When I say relatively prime, when I say relatively prime, so basically it means that so when two numbers are relatively prime, when two numbers are relatively prime, what this basically means that it means that the greatest common divisor between the two of them, that's their GCD, means that their greatest common divisor is what? Is 1. So let's take for example, when I take 3 and 5, for example, the greatest common divisor of 3 and 5, that is the number that will divide both 3 and divide 5 at the same time, is just 1. So they don't have any other factor that can divide the two of them except from 1. So it means that 3 and 5 are what? Relatively prime, because their GCD is what? Is 1. So basically I've explained what we call a unit for us, and I've explained what they call relatively prime. Now this theorem is saying that if an element A in modular integer n is a unit, that is A is in Zn is a unit, A is a unit if and only if A is relatively prime to n. They're asking us to prove it. Now let's look at this place and understand what this is saying. If you look at 1, 2, 3, and then 4. 1, 5, the GCD between these two is just 1. 2 and 5, the GCD between them is just 1. 3 and 5, the GCD between them is 1. 4 and 5, the GCD between them is 1. So you can see that the greatest common divisor of this unit together with this is just 1. And I basically said here that two numbers are relatively prime if the GCD between them is what? Is 1. That's why my answers is 1, 2, 3, 4. So basically, if they say what is the unit in Z10, by the time I write out all my residues, 0, 1, 2, 3, 4, 5, 6, 7, 8, up to 9, I don't have to draw this table before I know my unit. All I just need to do from this theorem, I already know that the elements here will be a unit of 10 if and only if they are relatively prime. And what are the elements that are relatively prime in Z10? 1, the GCD between the both of them is 1. 3, so I have 1, 3. I can't pick 4 because 1 will divide 4 and divide 10. 2 will divide 4 and will divide 10. I can't pick 5 1 will divide 5 and divide 10. Okay. 1, 3. I think 5 should be there. Yeah, 5. Yes. No, 5 isn't. 5 will divide itself and also divide 10. 6 can be picked. 2 will divide 6 and divide 10. 1 will also divide 7 and 9. These are the units in Z10. So basically, if I'm asked to find the unit in Zn, I'll first say the units in Zn are the elements that are the units in Z10 are the elements that are relatively prime to what? To 10. So then I can just write this out. This takes all of this. So now they're asking us to prove it. An element A in Zn is a unit if and only if A is relatively prime to n. So we start. So if you're asked to prove this, so we start by saying the proof. So we say suppose A is a unit in Zn. So if A is a unit in Zn, what that means is that A inverse is congruent to what? To 1 mod n. So what this means is that if A is a unit from here, A is a unit if it's relatively prime. And relatively prime means that the greatest common divisor between them is 1. So basically I'm saying that 1 is the greatest common divisor of this A and the other element. For example, now from here, I'm looking for unit in Z5 and I got 1, 2, 3, 4. So this A inverse represents all this. The A itself represents this 5. So this 1 means that the greatest common divisor between them is just 1. I'm just representing them in module. So let's recall for A comma B. So if A is congruent to B in mod n, what do they mean by A is congruent to B in mod n? It means they have the same greatest common divisor. That's what it means. So if A is congruent to B in mod n, this implies that A minus B, n will divide A minus B. Let's cast our mind back to modulo. If they said let's say 12 mod 6, and then then they say 6, let's say 6 mod 6. So if they ask me that are the both of them congruent, first thing I'll do is 12 divided by 6. This will be 2 remainder 0. 6 divided by 6, that will be 0 remainder 0. Now because they are having the same remainder, then I'll say that what? 12 and 6 are what? Are congruent together in what? In mod 6, because they are giving me the same remainder. So basically what it means is that this 6 will divide this 2. That's what I mean here. So this 6 will divide this. So when you see that two numbers are congruent in a particular modulo, then this will exist. So n divides A minus B, and this implies that what? A minus B equals to R times n. So this means that the first one I gave 12 and 6. So if I'm to write it here, mod 6, we saw that these two are congruent in this particular modulo. So that means that 6 divides 12 minus what? 12 minus 6. And basically what that means is that if I'm to transform it to this, that means that 12 minus 6 equals to 6 times something. That's the R I'm putting. The n here, this is my n, and this is my what? R. So 12 minus 6 equals to 6. So 6 times something, which is my R, will give me my value for this. That's basically what this means. So now that we understand this concept, let's now go back here. So if A and the element that is relatively prime to it is, okay, if this is true, and I've shown you that is A is congruent to B in mode N. So if I'm going to show this also in this concept, then that means that I'll have something like this. A inverse minus 1 equals to what? R times N. So I can bring this here, then I have A inverse minus Rn equals to 1. And this can be written as A inverse plus N open bracket minus R, which is equals to what? 1. Now, if they are relatively prime to N, that is if A and if A is relatively prime to N, if A is relatively prime to N, so what this means that A, N, they have their greatest common divisor between them is what? Is 1. So an element A in Zn is a unity and only if A is relatively prime to N. So if A is relatively prime to N, it means that their greatest common divisor between is what? Is 1. So Ax plus Ny equals to 1, and this will be Ax, this from here, A inverse plus N times minus R equals to 1. So I'm choosing here as X, I'm choosing here as Y. So Ax to the other side minus 1 equals to minus what? Minus Ny. Now when you look at this, when you basically look at this, you see that it's conforming to what we have here. So you have Ax minus 1 equals to N times what? Minus Y. And this basically means that what? N divides what? Ax minus 1, which is this. So if A minus B is equals to R times N, then this means that N divides what? A minus B. So this means that, and if N divides A minus B, what does that mean? It means A is congruent to what? To B. And if A is congruent to B, then it basically means that what? The greatest common divisor between them is just 1. So Ax is congruent to 1 mod what? Mod N. So if an element A in Zn is a unit, it means that A is relatively prime to what? To N. And if it's relatively prime, the greatest common divisor between them will be what? Will be 1. So we've been able to prove that. So when we are asked to show this, that prove that an element A in Zn is a unit if and only if A is relatively prime in N. So I gave an example using the modulo table, and then I gave another example without using the modulo table. So this theorem is a it's a correct theorem. All we just did here was just to prove the theorem. So okay, the next thing we want to do is to prove that every field is an integral domain. So every field is an integral domain. First of all, I think we treated integral domain, and I said an integral domain is a commutative ring with identity that has no zero divisors. So you can check the previous videos. And what is a zero divisor? So a non-zero element A is said to be a zero divisor if there exists a non-zero element B in R such that AB is equals to 0, or you say BA equals to 0. But mind you, those A and B are non-zero elements. So I think I made justice to that about integral domain and zero divisor. So basically what they are trying to now tell me that I should prove that a field has no zero divisors. Because if I want to define an integral domain, An integral domain is a commutative ring. A field is also a commutative ring. A field has an identity. Integral domain also has an identity. So what distinguishes these two is just that a field, every non-zero element in a field has multiplicative inverse, but this does not. So if I'm going to prove that every field is an integral domain, then it means that I want to show that this field has no zero divisors. So basically, what we are trying to prove here is that there exists A, B in F in a field with A not equals to 0, that is a non-zero element A, such that AB equals to what? Equals to 0. So if I'm to show that a field is an integral domain, then it means that I want to show that it has no zero divisors. So let's cast our mind back to what they call zero divisor. Zero divisor goes like this. That a non-zero element A in R, a non-zero element A, that is, this A cannot be 0 in R, is a zero divisor, if there exists a B which is also a non-zero element such that AB is equals to 0, or we say BA equals to 0. This is what they mean by zero divisor. Neither A nor B is 0, but when I multiply the two, it's giving me 0. Now here they are saying that an integral domain, if I bring out the definition of an integral domain definition is, an integral domain is a commutative ring with unity that has no zero divisor. So basically, when I say it has no zero divisor, then it means that one out of these two, so if A is a non-zero element, then B will be a zero element. That's what they mean by has no zero divisor. Because you already know that when we say zero divisor, it means that A is a non-zero element if there exists a B which is also a non-zero element, such that this is satisfied. So when I say it has no zero divisor, I'm basically saying the opposite. So that's what we want to do here. That's why I said with A equals to 0, not equals to 0. So I'm going to show that this B is equals to 0. So you know here, if it has to be a zero divisor, this B will also not be equals to 0. But for integral domain that has no zero divisor, is this B that I'll tackle. So I want to show that B is not equals to 0. And I'm also going to show that if B is not equals to 0, then A will be equals to 0. So F is a field such that A inverse is in F. Yes, I defined a field for you, that a field is a commutative ring with identity such that every non-zero element has a multiplicative inverse. So it always has a multiplicative inverse. So such that A, so this is what they call multiplicative inverse. There's difference between multiplicative inverse and additive inverse. So you remember we said it is a commutative ring with unity equals to 1. So this A inverse is coming from the fact that every non-zero element in a field has a what? A multiplicative inverse. So I want to show that this is an integral domain. So basically what I want to show is that it has no zero divisor. That's just what I want to show. So now, since A equals to 0, and I know that the multiplicative inverse will always exist, because they said for every non-zero element in a field there exists a what? A multiplicative inverse. I want to show that AB is equals to what? Is equals to 0. So multiplying both sides by the inverse, so AB which will be equals to A inverse times 0. So I can write A inverse A times B equals to A inverse of 0. So you know from multiplicative inverse, which is equals to 1, that would be B equals to what? Equals to 0, because this times 0 will give me 0. So B will be equals to what? 0. So I've been able to show that if A is equals to 0, that is A is a 0 element, B is also a what? 0 element, such that what? AB is equals to 0. Also, I'm going to also do the converse, that is if B is equals to 0, A should also be equals to 0. So also there exists A comma B a member of F with B equals to 0, such that AB is equals to 0. So remember, you are trying to prove that if you want to prove that a field is an integral domain, you need to know what they're asking you to do. So integral domain means it has no zero divisor. So I want to prove that a field has no zero divisor. And when I'm saying it has no zero divisor, it means that this A and B are both zero elements. They are not non-zero elements, unlike the definition of zero divisors. So now since B is not equals to 0, then it means that there exists is what? Multiplicative what? Inverse. Remember that a field is a commutative ring with unity or with identity, such that every non-zero element there has a multiplicative inverse. So you must always bring in this multiplicative inverse here. So this implies that following this, so this implies that B, so here B inverse times AB equals to B inverse times what? Times 0, and this will be B inverse times BA equals to B inverse times 0, and I can write this as B inverse times B times A equals to what? Equals to 0, because this multiplied by 0 will give me 0. So B inverse times B, from definition, I can just write the definition here. By definition, B times B inverse, which equals to B inverse times B, equals to what? Equals to 1. So this will be 1 times A, that's A, which will be equals to what? Equals to 0. So I've been able to show that first thing, if A is not equals to if A is equals to 0 and B is equals to 0, AB is equals to 0. That's has no zero divisor. And I was also able to prove the converse, because you cannot just tell me that A equals to B equals to 0. You must also show that what of if B comes first, what happens? So I needed to show that if A is equals to 0, B is equals to 0, AB is equals to 0. If B is equals to 0 and A is equals to 0, then what? I can say BA equals to what? 0. So I've been able to prove that every field, so therefore F has no zero divisors. So since I've been able to prove that F has no zero divisor, and I know that an integral domain has no zero divisor, I've been able to show that every field is an what? Is an integral domain. Now, before I move to what we want to do associate, I'm going to write out some important rules on the board. These rules will cover some of the stuffs we have done in the previous classes on zero divisors, integral domains and all. So the first one is that the zero divisors of Zn are what? Are precisely the non-zero element, that are not relatively prime, to what? To n. So let's take for an example. If they ask me to find the zero divisors in Z8, I know if I'm to write out the residue of Z8 is from 0 to. So without stressing myself, if I want to know the zero divisors of Z8, all I will just do is to go to the residue. What are the elements in this residue that are not relatively prime? And when I mean not relatively prime, remember from what I showed the other time, that when I say something is relatively prime, it means the greatest common divisor between both is just what? 1. That is, the highest number that can divide both is 1. So when I now say are not relatively prime, it means that the greatest common divisor is not 1. So the zero divisors in Z8, zero divisors will now be what? Will be 3, 5, and 7. So let's take another one. So if I'm to pick 2, 4, 6 are the what? Non-zero, are the non-zero divisors. Okay, these are the zero divisors, and I think this should be the, so it should be 2, 5, and 6, not 3, 5, 7. 2, 4, 2, 4, and 6. Because 2 and 8 are not relatively prime. 1 will divide 2, 1 will divide 8, 2 will divide 2, 2 will divide 8. 2 will divide 4, will divide 8, 4 will divide 4, will divide 8. 2 will divide 6, will divide 8, and okay, 2 will divide 6, 2 will divide 8, 1 will divide 6, 1 will divide. So you can see that they have more than one factor. So the greatest common divisor between this element and this particular end here is not 1. So they are not relatively prime. So that's rule number 1. Number 2 says if P is prime, then ZP has no zero divisors. So basically what they are trying to tell you that if your P is prime, that is, these are P. If you have Z5, Z3, Z5, Z3, Z7, you know what are prime numbers now? Prime numbers are numbers that have only 2 factors, 1 and itself. So if P is prime, then it has no what? Zero divisor. So take note of that. And then the last one is that if P is prime, then ZP will have what? Integral domain. ZP has and what? Integral domain. So these are some of the important tools that we have to take note. It covers some of the things that we've done. So these proofs are also very, very essential. They might bring them out in the exam. So you look at the trend and then you can solve. So the next thing we are going to go down to is what we call associates. So okay, the next thing we are going to move down to the next thing we are going to move down to is what we call associate. So first thing first is I'll define what an associate is. So an element B in R. So basically what they are trying to say that there are different things in a ring. In a ring we have units, in a ring we have associates, in a ring we have integral domain, in a ring we have zero divisors, in a ring we have field, and so on like that. So we are basically taking some sub-elements inside a ring. So an element B in R is called an associate. It's called an associate of C in what? In R. If B is equals to UC for some units, uh, U in, so for some units U in R. So let's take for example, we were asked to find Find the associate, of 4 in Z10. I want to find the associate of 4 in Z10. The first thing I need to find are the units. What are the units in Z10? The solution. So there are two ways to find the units in Z10. Either you use your modulo diagram, you write 0 to 10, something like this. 0, 1, 2, 3 to 9. Here you also have 1 to 9. Then you start multiplying. Now, then when you multiply, whatever gives you back 4 here, those elements are the units in Z10. But doing that will actually waste my time. I already know that the units in Z10 are the elements that are what? Relatively prime to what? To 10. I think I've mentioned that. That was the first thing I proved. That if A is a unit in Zn, then it basically means that what? A is what? Relatively prime to n. So what are the units? What are the elements that are relatively prime? So we find the unit in Z10. And if I'm to write from 0 to 9, the unit in Z10 will be 1, 3, 7, and what? And 9. Because when you look at this 4, the greatest common divisor between this and this 10 is just 1. If you say 2, there is something common between 2 and 10. 1 will divide 2, 2 will divide 10, and 1 will divide 10. 2 will divide 7, and it also divide 10. So you can see that the greatest common divisor between them is not just 1, it's 2. When you look at 4, the greatest common divisor between them is 2. When you look at 5, the greatest common divisor between 5 and 10 is 5. 6, greatest common divisor between them is 2. 8, greatest common divisor is 2. So basically, and when we say something is a unit in a particular Z and is relatively prime, their greatest common divisor must be 1. So all of these 4 compared to this and this 10, 1, 10, the greatest common divisor is 1. 3 and 10 is 1 that can divide both. 7 and 10, 9 and 10. So that's why we have this 1, 3, 7, 9. Then what we now do is we follow this instruction, that is B equals to UC for some unit in R. So now that we have found the units, we are looking for the associate of 4 in Z10. So we start by saying 1, which is my unit, this U, 1 times my C here is the associate, that's 4. 1 times 4 will give me what? 4. This is one associate of 4 in Z10. So U, the next one I pick is 3 times my C is still my 4. 3 times 4 will give me 12. But 12 in Z10 will be remainder what? 2. Then I pick 7. That's my unit. And then C is my associate, which is 4. 7 times 4 will give me 28. Yes, 28. In 10, remainder what? 8. Then I pick 9 times 4. That will be 36. 36 in Z10, that will be what? 6. So basically, it means that the associate of 4 in Z10 is what? 2, 4, 6, and what? And 8. So you can do this yourself. Find the associates of 5 in Z12. So find the associate of 5 in Z12. So basically what you have to do is to first find units in Z12. That is elements that are relatively prime to what? To 12. That's 1. 2 is not there. 3 is not there. 4 is not there. 5. 1, 5, 7. And I think 11. 1, 5, 7, and 11. And when you find the unit, then you follow this route, you are going to get your associate of 5 in what? In Z12. So let's not waste our time. The last thing I'm going to do here is I want to prove that these associates follow what we call equivalence relation. If you remember your equivalence relation, these are what you've done in your abstract algebra 1, where they said RST, reflexive, reflexive, that means that A can map into itself. Reflexive, symmetric. Symmetric means that what? A star B implies that what? And then transitive. Transitive. This means that if A related to B and B is related to C, this implies that what? Implies that this A is related to what? C. So we want to show that this associate follow this equivalence relation. You can ask us to prove it. That show that an associate, or you can say prove that a relation follows the equivalence relation. Prove that the associate follows it. That is what they are basically saying, that one, A is related to A. B, if I'm using the definition of associate, if A is an associate of B, then B is an associate of A. If A is an associate of B and B is an associate of C, it implies that what? A is an associate of what? C. So if I'm going to take them one after the other, first thing first is I'm going to prove the first one. One, prove that A is an associate of itself. That's number one. And element B now is called an associate of C now if this occurs. So I want to prove that an associate follows this equivalence relation. So using this definition, this basically means that A is an associate of itself. So number one, so, and it's true. When you look at 4 here, you see that 4 is an associate of itself. We got 4. When you do this too, you are also going to get 5. 5 is also an associate of itself. So number one, any element A is an associate of itself. So I can change A is equals to 1 times A. Now without wasting my time, 2. I want to show that if A is an associate of B, if A is an associate of B, then what? B is an associate of A. Then B is an associate of what? Of A. Let's prove this. So I will start by saying, let's just suppose that B is an what? B is an associate of A. What does this imply? It means that B is equals to what? UA from definition of associate. If B is called an associate of C, then this implies. So if B is an associate of A for some unit, B, where U is a unit in what? In R. Now, if I multiply both sides by its inverse, I'm going to have U inverse, this U, times B equals to U times A times U inverse. And then, so you have B U inverse equals to U times U inverse times A. From definition of multiplicative inverse, that will give you what? 1. That will be 1 times A. So you have B U inverse equals to what? Equals to A. So this can imply that A is equals to B U inverse. So I've been able to prove that if B is an associate of A, then what? A is an associate of what? B. I can write this thing by A equals to U inverse and what? And B. So therefore, A is an associate. A is an associate of what? Of B. So if B, suppose B is an associate of A, so I've been able to prove that A is an associate of what? Of B. Now the third one is that if A is an associate of B, if A is an associate of B, comma, and B is an associate of C, and B is an associate of C, then this implies that what? A is an associate of C, then A is an associate of C. Let's prove this. So let's take the first statement. If A is an associate of B, what does that mean? It means that A will be equals to what? U will be equals to UB, where U is the unit. where U is a unit in R. And B is an associate of C. So if B is an associate of C, that will be B equals to VC. I don't want to use same unit. So I'm using something else where V is a unit in what? In R. So I have equation 1 here and I have equation 2 there. Now A is an associate of B, B is an associate of C. What I want to prove is that what? A is an associate of DC. Now you can see that B is equals to VC. I can say equation 2 into equation what? 1. So we substitute equation 2 into equation 1. So when I substitute equation 2 into equation 1, I have A equals to U multiply my B is what? VC. So I can say A equals to UV times C. So when I multiply a unit by a unit, it will give me what? A unit. Now, this will be A equals to what? UV times C, since multiplication of 2 units is also a unit. So let's assume that this U and V are a number that we know, a defined number that we know. So this is a unit, this is a, if I multiply, they give me a particular unit times C. So I've been able to prove that what? A is an associate of what? C. So therefore, A is an associate of what? Of C. End of proof. So this is an associate, and I was able to give you the associate of a particular element in Zn. This is Z10, and I gave you a very short form of finding the associate in Zn. I gave you work to do, and then I proved that this associate follows this equivalence relation from your RST: reflexive, symmetric, and transitive. Reflexive means that what? A goes into the step. A star A will give me A. Symmetric is if A is related to B, then B is related to what? A. The transitive is that A is related to B and B is related to C. This implies that what? A is related to C. So all of these three, we brought it into associate, and we said that A is an associate of itself, and we were able to see here from the example I gave that when they said find the associate of 4, we were getting 4 also to be an associate of 4 in Z10. So this is true. So any element A is an associate of itself, since A is equal to what? 1 dot A. So symmetric, if A is an associate of B, this implies that what? B will be an associate of what? Of A. So if we are able to show this, so suppose B is an associate of A, we started from A. So let's assume that B is an associate of A, then we multiply out by its multiplicative inverse, and then we add this. This U inverse is also a unit. It will also be a unit. So since in an element we don't just have just one, we have multiple units. So you can see that it's not just one we are having, we have like 4. So this might represent another one. So A equals to B times its unit, and this implies that what? A is related to B. So if B is related to A is related to B similarly. So you can even start from, let's suppose that A is an associate of B, and then you end up proving that what? B is an associate of A. Then the third one, which is the last one, if A is related to B, that is if A is an associate of B and B is an associate of C, this implies that what? A is an associate of C. So I started with my equation 1, my equation 2, then I started equation 2, equation 1, and I was able to prove that what? A is an associate of what? Of C. So this brings us to the end of today's class. So in the next class, we'll be talking about subrings and ideal. So I would love you to share and like the video and drop your comments about whatever you don't understand, so that we can treat it in the next class. So thank you.